In this video, we're going to look at electrolytes, specifically strong electrolytes. In general, an electrolyte is any solution that conducts electricity. In order to conduct electricity, you need moving charges. We're going to look at ionic compounds in solution. When ionic compounds are in solution, we're going to form ions, which are charged particles. And if those charged ions can move, we can conduct an electric current. So here's what happens when you put an ionic compound in water. The compound will dissociate and separate into ions. So key word here is dissociate. Dissociate means to separate. There are already ions present in the compound that were formed from the transfer of electrons, so all we have to do is separate those ions so they can float around in the water, and boom, we can conduct electricity. We have moving charged ions. Now, to separate the ions from the original solid crystal, the water molecules will be attracted to the ions in the original ionic compound. And watch what happens. So we get this maybe positive sodium ion. It becomes completely covered in water molecules. And check out the arrangement of the water molecules. If I have a positive ion, it's the negative oxygen end of the water molecule that will surround that positive sodium ion. And soon that positive sodium ion will become completely engulfed in water molecules so that it just completely removes from the crystal. And you have this free-floating sodium ion that is covered in water molecules. And look at the arrangement again of these water molecules. They're all arranged negative oxygen attracted to the positive sodium. We call this the shell of hydration, where an ion is completely covered in water molecules. Something similar happens with the negative ion. Here we have a negative chlorine ion. It becomes covered in water molecules, but it's a little different arrangement. This time it's the positive hydrogen ions that are attracted to the negative chlorine. Oh, cool. And we have another shell of hydration. Now these ions are very stable in solution. They'll never come in direct contact with each other. The chlorine and the sodium are always covered with their water molecules. So unless I evaporate the water, the ions will never go back to the original solid. But obviously that can happen if we simply evaporate the water. Then the positive sodium, the negative chlorine will be in direct contact with each other again. Now we say that ionic compounds form strong electrolytes because they have a high tendency of forming ions. In fact, we say that it's 100%. 100% of the ions in the original solid will form these hydrated ions in solution. So there will be no neutral molecules. Everybody dissociates to form these hydrated ions, which just means that it's an ion that's covered in water molecules. That's what we mean by a strong electrolyte. And the more ions in solution, the more electricity we can conduct. Notice too that the water molecules never change. They're always H2O. So watch what they're going to do in this next example. They want us to write an equation for the dissociation of the following ionic compounds in water. So number one, check out what's in the solution. It's all ions. Everything is ions. There's no neutral molecules. No neutral molecules of HCl, no neutral molecules of NaOH, sodium hydroxide. Everything has split to become ions. That's what we mean by a strong electrolyte. 100% formation of ions. So if I wanted to write an equation, it might look something like this. Dissociation would just be the HCl that separates into hydrogen plus 1 and chlorine minus 1. That is dissociation. And dissociation is a physical change. Because all we have to do is evaporate the water molecules from those ions, and boom, this thing shifts backward and we form the original HCl molecule. Don't confuse this with decomposition. Do you remember something like this? 2 HCl that decompose to form like hydrogen and chlorine gases. That is a decomposition. Which is a chemical change. I mean, that exists, it's totally fine, but it's not what we want to do when we form a solution. In order to reverse the second equation, you'd need another chemical change. We'd need a synthesis of hydrogen gas and chlorine gas to form the original HCl compound. So it's fine, it exists, it can happen, but it's just not what we want to talk about in solution formation. Dissociation is just the splitting into ions, and we do have to put those charges in. So let's say I wanted to do the other one, the sodium hydroxide. I would have my NaOH that dissociates to form sodium ions and hydroxide ions. You do not need to split the polyatomic. You can leave hydroxide as the ion. And so again, we've said that this is our 100% dissociation. This happens 100%. All the molecules split. So for example, let's say initially I have 100 molecules of NaOH and 0 ions of sodium and 0 ions of hydroxide. After dissociation, this would be my final conditions. These are gone. 0 molecules. And you'd have 100 sodium ions, 100, and 100 hydroxide ions. That's kind of what we mean by a 100% formation of ions. Everybody splits. A couple other examples. We're going to look at a lot of these in the lab, and we're going to test their electrical conductivity. Here they ask me to write dissociation equations for the following chlorides in water. So the sodium chloride would simply just be sodium chloride splitting into sodium ions and chlorine ions. We do have to put the charges in to show that they are ions. They are charged particles, and that's why the solution can conduct electricity. Calcium chloride. There's a couple ways you could write this. CaCl2 would split. We'd form the calcium plus 2 ion, and we'll have 2 -1 chlorine ions. There's one option. Or you might see this written as calcium plus 2 plus 2 chlorine ions. You could put the 2 out in front. The 2 out in front means that you have 2 separate chlorine ions. Either of these options are great. Happy face, smiley face. But caution, here's something that would not be acceptable. And it's commonly missed. So this is my sad face. Number one, we need charges. We didn't include that the calcium is formed as calcium ion. If I just leave it as Ca, that's understood to mean elemental solid calcium. When we put the ions in with the charges, I mean, if you really needed a phase symbol, it would be aqueous, dissolved in water. This chlorine ion would be aqueous. If I put Cl2 like diatomic chlorine, that's elemental chlorine gas. And again, that's not what I want here. I want chlorine ions in solution. This is the decomposition of calcium chloride. And again, it's fine, it exists, it can happen, but it's not what happens in solution. So if we put the little 2 down here as a subscript, then that shows that the 2 atoms are joined together in a chemical bond. I don't want that. I want 2 individual chlorine ions. So kind of similar with the aluminum chloride, we'd probably go aluminum chloride splits, dissociates to form aluminum plus 3 ions. And then I usually just put the 3 out in front. 3 chlorine ions, -1. The more ions formed, the greater the electrical conductivity. So if I had to rank these and decide which would conduct the most electricity, it's just the one that forms the most ions. So if I look at sodium chloride, I get 2 moles of ions. Calcium chloride gives me a total of 3 moles. I get the calcium and 2 moles of chlorine. Aluminum chloride gives me 4 total moles. The aluminum and the 3 chlorine. This is my winner. I would have the most ions. Most ions formed in solution. And again, we're going to go in the lab and test a lot of these so that our prediction on paper can be proven with lab data. We'll look at electrical conductivity using conductivity testers. It's going to be great.